extensions of what we have considered, which was the question of the tunneling in the double well, and it's just very superficial to give you an idea where this, what we discussed, will appear later on in quantum field theory. So the first is just still a quantum mechanical problem, it's just an extension of what we did, and the second short example is already like trying to give you some taste about what we then next week or after the week are going to start discussing quantum field theory. Okay, so this is then going to higher objects. So this is first example is just an extension of what we did. The other one is in the end only words, but I also hope that you can get the idea that it's like giving you some motivation to follow the second question. So the first thing is just to consider instead of the double well problem, let's say a meta-stable minimum. And this, I mean, happens a lot in physics. Like you can think of this as being, let's say, an unstable nucleus, or in spin glasses, or generally glasses. Actually, you have this kind of problem where you have potential, which has maybe some local minimum, but this is not, say, the global minimum. So you can be, again, if the kinetic energy is much smaller than, this should be, than the height at 0, so we should put it here 0, you can be stuck, or a particle with kinetic energy much smaller than the barrier can be stuck in this minimum. And the question is, well, does the particle stay here, or does it notice that it's not the true minimum? Does it relax then to the true minimum by tunneling through the barrier? Okay? This appears instead of solving many problems. So what here you typically want to know is what is the lifetime of the particle, or what is the survival probability of a particle being captured in a metastable minimum. Forgot, I put it away, but in the last estimate, again, I made a stupid mistake. I mean, we made the estimate for the time divided by the typical number should be much larger than 1 over omega, and not than omega, so it was. So that's the question we want to answer, and well, what we should then calculate again is the probability to now make a transition from here to here. Okay, so by what we have systematically, what we have done before, so this would be the problem. You're, let's say, stuck in this minimum, and you want to ask what is the probability to tunnel here. So we can just, to calculate this now, we can just do the same trick as we did before. So one can change to the same question in imaginary time, to invert the potential. So there, the minimum becomes a maximum. And what you're considering then are classical solutions of the particle, so which would here correspond to tunneling process, are then actually those processes, it's called as QM, the position of the minimum. So the particle, the classic solutions are now those where the particle departs from the top, then goes through the minimum, goes up here, and then just bounces back on this potential, okay, and then follows back again here, okay. So what you have to calculate then is just the same calculation that we did before. So again, you can identify structures which are well defined in time, and I just give one example. So you have time tau prime, And you start from a configuration where the particle sits in M, which is the maximum, and then it will make transition, bounce somewhere here, bounce back, and stay at this at the maximum again. So what you can do is you can just do the same calculation where you now sum over these bounce solutions. So you can express again your transition amplitude in imaginary time now as a sum of all possible bounce solutions and multiple bounce trajectories. So I just briefly outline this. So if you like, you can look at this in more detail. So multiple bounce trajectories are possible, meaning that for the classical or the semi-classical calculation of the transition amplitude, now actually what we're here interested in is the probability to stay in the minimum. So this would correspond to the survival probability, and also the amplitude starting at Qm after some time, just now imaginary time, is still in there. So this is the survival amplitude. To square this, you get the survival probability. This can now be again expressed as a sum over all possible bounces. So every bounce has some action, and again you can position this action where you want to. You can make the loop bounce approximation. So the only difference in the calculation now is that before we had the sum over n instantons, where n had to be odd because we said we want to propagate from one minimum to the other. Now we have the entire bounce is given by a typical time scale which we assume to be small, and we can sum over all possible bounces. Okay? So instead of having the sum over all odds, we have a sum over all, which means like our sine hyperbolicus now becomes an exponential. So if you do the calculation, you arrive at a very similar expression as before. The only difference that now we have here the exponential of the imaginary time tau. There's the parameter of our ignorance, and then this is the, let's say, the price you have to pay for bounces, again given by the classical action of the bounce, which is independent of the time when it happens. And well, then what you have to do is you have to do the analytic continuation, which you can again do. Now here it's important that this parameter k, so if you really do the calculation, it's purely imaginary. So, and physically this has to be, because if you then do the analytic continuation, you get again a dynamical phase factor, and then you get an exponential suppression on the time t. So this, after analytical continuation and squaring, despite this. So if you then look at the probability, H bar, the survival probability is the probability that after the time t, under the dynamics, you're still where you started. This is then proportional to some parameter gamma, which is then the typical escape rate for the problem times t. And the escape rate here is then given by, so k is purely imaginary, then it's given by the absolute value of k, and you have again that this rate depends on the bounce action divided by h bar, and this is escape rate. So this is one extension of the problem, which can be calculated very similarly, and which gives you the escape rate from some metastable minimum. And the second example now comes, instead of looking at the quantum dynamics of a zero-dimensional object, just an example from classical mechanics. Classic phase transition. Questions here or? Okay, so this is the second example. Using again the same arguments before, just interpreting the objects in a different way that appear. Okay. Like the nice thing about particle. So this is some classical phase transition. And just to comment on what's called the non-environment theory. And this is now just, I mean, trying to give you an illustration. Okay, let's see. So, what you can consider is, let's say, problem of classical magnetism on a lattice. Let's call it like this, and what I mean by this I will tell you. Let's consider some d-dimensional lattice. Which is given here, and on each of these lattice points you can put some degree of freedom, which I call Si, and this is just a number which is 1 or minus 1, and we can think of as some spin pointing up or down. Okay? So this is just a classical number, and we can think of like configurations where on every point in space you can attribute a number of 1 and minus 1. What we want to think about is this kind of some kind of magnet which can point into 2 directions. Okay? And then we want to give each such a configuration and some energy, and this is here now given by the d-dimensional Ising model. So the Ising model here refers to the fact that you look at degrees of freedom which can take like the 2 values 1 and minus 1. And d-dimensional here refers that here I draw a 2-dimensional system, but this is general for, let's say, d-dimensional lattice. And this is given by the Hamilton function, so we have some configuration of, let's say, call them spins fixed. At every point in space we have a value 1 or minus 1 pointed up and down, and we can attribute to this configuration an energy which depends on the configuration, so we sum over all I and j here and multiply Si with Sj and some number Cij, and then let's say we have some external field which I call H, and which only measures the total value of S. Okay, so what we can think of, like this Cij describes, or typically depends only on the distance, describes the interactions between the spins. And the field, you can think, H, you can think of some external field. Okay, so this is one model for magnetism, which tells you this is a term which likes to introduce some order into the problem. Depending on the value of C, they want to be just all aligned. Okay, and then there is some field which also may give you some preferred direction to spin on the. So this is one model for magnetism. And what you can now study is like the properties of this model by looking at, let's say, thermodynamic properties. So what you typically are interested is, as a first starting point, to look at the classic partition function. Classic partition function. So in this case, this is given by the sum over all configurations that you can have, and every configuration just gives a weight which is given by the Boltzmann factor minus beta, which is the energy. So it's Ij, it's I. Okay, so this is a very typical problem that you're interested in. Like problem here for, let's say, one model for magnetism, where the spin is a classical degree of freedom, so we are not dealing here with operators, but it's just like numbers like pointing up and down. So this would be the classical partition function for the d-dimensional Ising model. Okay? So what I don't derive now in detail, but what I don't just tell you, maybe make an exercise, or maybe we will discuss this in the lecture. You have to see that you can, starting from this partition function, you can derive a low energy theory for this. Okay, so you can, by doing some tricks, which we will all discuss in detail, maybe we then come back to this, you can map this problem to now a problem where you introduce a new degree of freedom, which also tells you about the magnetization in the problem, like if you have here an average value of SI, that will correspond to some finite magnetization, but which now only takes into account low energy content. And I just write down the action, and I mean, to believe me, that this is what it is. So you get some integral over now some continuous field. So this is again partition function would now correspond to a field phi, which depends on the coordinate x to the d. You make some continuum approximation. So in the low energy theory, you shouldn't care too much about like lattice structures and whatever. So you can make some continuous approximation, and you can write an effective action which has again the form of the sum of all configurations, and you give each configuration, you give a weight of the Boltzmann form, where now just write down this effective weight factor of the classical Landau type. So you can derive such a contribution, where it's one term that wants to suppress like spatial fluctuations, and then there's an energetic term that depends on the configuration phi. So this is all depending on the d-dimensional coordinate, which typically has a quadratic and a quartic term. Now for stability, this quartic term has to have a u which is positive, and the t being positive or negative now brings you the interesting physics. Okay, so this is determined by these parameters k to u, which are related to the microscopic parameters. And again, there's a generic way how to derive this kind of low energy effective theories. But if you just look at this and now look at what we, what did we arrive at? We arrived at a partition function given by d-dimensional objects, okay, which has some wave function here. Now, if we would specify to the one-dimensional case, this would correspond just to one-dimensional objects, like which is exactly what the paths are. Okay, so in the 1D case, we would sum here about like all the possible like one-dimensional lines, where each configuration is given by a derivative second order. So this line here is like configuration in space, but if we would interpret space as a time coordinate, this line would correspond to the path of a zero-dimensional object. Okay? And then this derivative here would correspond to the time derivative, so this would just correspond to the kinetic energy part in the action, and this would correspond to a potential. Now this would be q squared q to the 4th. So this potential is either this way or it's this way, depending if t is larger than 0 or t smaller than 0. Okay? So we see that if, for example, t is smaller than 0, the partition function for the effective theory of this one-dimensional magnet is just exactly given by the same expression that we had to look at for studying the transition amplitude of a one-dimensional particle in a double-weld potential. Okay? So, independent of the dimension, you can see if you now do to this object what we do in the semi-classical approximation. In some way we said if the typical action accumulated along a path is larger than h bar. So if the energy scale here is larger than 1/, temperature, oh, I didn't say that beta is 1/, temperature. Then we could here also start out from some saddle point mean field approximation. So we should look at optimal configurations by looking at minima of this contribution. So if we would do this, look at the minimas and say, well, we see that all spatial variations are suppressed, so let's look just at the constant contribution. We will see that, well, depending on the value of t, we will find or that the constant solution which minimizes the energy is just being 0, or if t is 0, it can be, let's say here, phi being minus a or phi being plus a. Okay? So we have a finite value at the mean field level for phi once this becomes smaller than. Now what I have to tell you is that this finite value would correspond to finite magnetization, so this would correspond to some magnetic phase. Okay? So what you just have here is the problem that you see that depending on the parameters, what can happen is that you can break some symmetry. So what is meant here, you start out from a problem where, let's say here the potential is completely symmetric under reflection, but once you have t smaller than 0, let's say here you break this kind of symmetry by choosing one of the minima. Okay? And the question that you want to ask then typically is saying, well, if t is smaller than 0, your mean field analysis would just say you end up with a configuration which has a finite, mean field value. So this would be like an order parameter for phase condition, which you would be related to. So the question is if this here is stable or not, if fluctuations will destroy this or not. Okay? So what we considered in the path integral were just quantum fluctuations in imaginary time. Now here we are considering a purely classical problem because we started out from something which already didn't have any operator, but just kind of a classical field pointing up and down. And this is like a classical partition function, but we have thermal fluctuations for a given temperature. And the question then is, well, is this, if you choose one of the minima, is this a stable configuration or is this destroyed by fluctuations, by thermal fluctuations? And what we just calculated in the zero-dimensional path integral problem was that we saw, well, when you're stuck in here, in time you will have these instanton solutions which will just tell you that you will tunnel around and you will always tunnel quite substantially. So here, this would correspond then to, like this multi-instanton configuration would correspond now to, this would be the phi variable, and this would be like the constant, no, not the constant phi variable, but this would be the phi variable. This is like the space coordinate x, which before was time. So you can say, well, you're in one of the minimums at minus a, but then there will be configurations that we should take into account where parts just break up and go to the other configuration. Okay? So if you have that these configurations start to proliferate, to become that they are not restricted, like that they're very much suppressed, they will just start to disorder your system. Okay, so it's not right to just think of, well, the variables always at let's say -8 all over the place, so it's not a homogeneous mean field configuration which describes it right, because you have the thermal fluctuations which break this up and will contribute to this partition function. So this partition function here is not dominated by the mean field value corresponding to phi being constant plus or -8, but it's actually dominated, it can be dominated by these solutions where just this breaks up and you have this, in the end, disorder condition. So if these give a substantial weight to this partition function, you see that your order is destroyed. Okay? So you do not have a phase condition. And now comes the thing that I said in the beginning. So the only mechanism that drives like this kind of transition, why it's good to break up. Well, if you break up, you will pay some price for it. It will be energetically costly to break this up here. Yeah, you will pay some price. So in the case of the tunneling, this was the instanton action. Pay some price, but you gain, because you can break this up now in many ways. So you have an entropic factor, like phase space volume. You can set this boundary wherever, and you can break up in many pieces. And the only question always you have to ask is the entropic factor, like the phase space that you have, is this overweighting the energetic price that you have to pay for such a configuration? If so, you will not end up in a symmetry broken phase, but the symmetry will be restored. Okay? And what we saw in the quantum mechanical problem is that actually so what we saw is that these instantons play an important role. Okay, so just relying on this analysis and making the analogy, well, that this maps to this problem, which in d equals 1 is actually exactly what we're considering. We notice that, well, in d equals 1, we expect that these configurations will always contribute to the partition function. They're important, they will disorder the system. So in the d equals 1, we find that such a symmetry broken phase is not allowed. Okay? And this is depends crucially, like this kind of arguments will always appear, like, is it possible to break some symmetry or not? And the game is always, well, does entropy, the entropic factor, give you enough to overweight the energy cost that you have to pay for disordering the system? And now there's different variations of the problem. So we see, first of all, the dimension will play a role. So, like if you break up, for example, here's such a phase, you can think of like this as a boundary, let's say, of spin up and spin down, so you pay some price. Now it depends on the dimension of the system, like how the boundary scales with, also here you could get some points, in one dimension you can have scale with some line, and so on. So dimension enters. Now this was the problem for a classical system, so where we start out with some classical fields. If you start out with spins being operators, you will write a partition function not in this way, but you have in the same way as we constructed the path integral for the quantum problem of the zero-dimensional object, you will just increase the dimension here by 1, taking into account quantum fluctuations. And then there's also a question about like, what is the symmetry you're breaking? Is it a discrete or continuous symmetry? And there is then some theory, which is the Mermin-Wagner theory, which tells you, like in general, what is the lower critical dimension in which you can break a symmetry, depending on if it's continuous or discrete. And all this we will probably not come to, but this would be something, I mean, a natural thing. So what we will do, like in the next lectures, is start to the many-body problem, formulate like the the path integral formulation for the quantum-partition function, and then discuss various examples how to derive effective theories. Now for this we have to know how to do perturbation theory, introduce some general way how to derive these effective theories. Now the next point then would be the analysis of this effective theories using, for example, RG arguments, but I don't think we will get there. So what we will do next is just discuss various effective theories, how to derive them. Okay. And then Thursday, I think everyone was here, no? Thursday at 10, and then